Hello everyone, it's my pleasure to welcome you to today's presentation that I titled Use of Water Disinfectants and Implications of Byproducts. My name is Omenya Maxwell, Department of Physics, Environmental Geophysics Option, Covenant University of Ogun State, Nigeria. These are my email addresses. A few weeks ago, I put you through particle sedimentation in water and the forces acting on it, and as well settling velocity, especially towards the vertical and horizontal component. Today we are going to look at water disinfection, chlorine as the widely used disinfectant, chlorination, byproducts from disinfection, how the byproducts are formed, disinfection kinetics. Now, what is water disinfection? It simply means the removal, deactivation, or killing of pathogenic microorganisms in contaminated water. Pathogenic microorganisms are destroyed or deactivated, resulting in the termination of growth and reproduction. So, when microorganisms are deactivated, it will affect the growth and the reproduction of such organism in the water. When microorganisms are not removed from drinking water, it poses terrible health risks to human and possibly lead to death. The most widely used disinfectant is chlorine. It's often used to provide residual disinfection in the distribution system, especially in pipes where water treatment passes through, and as well distributes to the public for consumption. So chlorine is one of the disinfectants that is used to handle water that is to be distributed for public use. The process of adding chlorine to drinking water for disinfection is called chlorination. Now, the chlorine is available as a compressed elemental gas. It is as well available as sodium hypochlorite solution and solid calcium hypochlorite. So chlorine can be in these three forms. Now, chlorination, which is addition of chlorine to water. Now, we are going to discuss this in three forms. How chlorine can be added in water and what some of the conditions that must be met before a particular method can be applied for water treatment. Now look at the chlorination in plain water. This is the addition of chlorine in the tank or reservoir that contains water. The amount of chlorine to be dosed is 0.5 ppm. This can only be done after water treatment and discovers that the water turbidity is less than 20 to 30 nephelometric turbidity unit. So if the turbidity is greater than 30 NTU, there is no need to apply this kind of method. Now, pre-chlorination. This is the first point of treatment using chlorine before the water passes through other treatment processes. So at this first point of treatment, the amount of chlorine to be dosed is between 0.2 and 0.5 ppm. This will help to reduce the microbial load in the water. And if the microbial load is reduced at the early stage of treatment, then other processes will be at a reduced level to require minimal treatment processes at the upstream. Double chlorination. This is when chlorine is dosed at the pre-treatment, the beginning of the treatment. Chlorine is dosed, and as well dosed at the end of the treatment, which is post-treatment. So that's why we tag it before and after. So when you dose chlorine at the early part of treatment and after treatment, it is called double chlorination. This is used when the water to be treated has the following: high turbidity. The turbidity is very, very high. And as well, if the water is highly polluted, then it requires pre-treatment using chlorine, and as well post-treatment using chlorine. Then post-chlorination, this amount of chlorine is dosed after all the treatment processes. This is as well called residual chlorine. That's the amount of chlorine that will be serve as the leftover in the water after treatment. So the amount should not exceed 0.2 milligram per liter or ppm. The contact time is between 15 and 20 minutes. Now, this is the point where we're going to dwell much today: the byproducts from water disinfection. The type and amount of disinfection byproduct produced during water treatment depends largely on the following: the type of disinfectant, that is to say, if you are using ozone as a disinfectant, the byproduct will be different from that when you are using chlorine dioxide. So it depends on what or the type of disinfectant you are using. That will determine the type of byproducts that will come up. Another thing is water quality. If the water is highly contaminated, the byproduct will be different from when the water is slightly contaminated. Another thing again is treatment sequence. If the arrangement of the treatment is different, then the byproducts as well must be different. Like the treatment process for groundwater differs from that of surface water. So expect different byproducts. At the same time, contact time is another thing. The contact time for ozone is just 4 minutes. So it will have a different byproduct from that of chlorine that takes 20 minutes and above. Another thing to be considered is environmental factors such as temperature and pH. Like the groundwater pH is quite higher than that of the surface water. What are the disinfection byproducts? Byproducts that originate from halogenated organics such as trihalomethanes, haloacetic acids, haloketones, and others that are produced primarily as a result of chlorination. Another aspect is organic oxidation byproducts such as aldehydes, ketones, assimilable organic carbon AOC, and biodegradable organic carbon BDOC that are associated primarily with strong oxidants such as ozone, chlorine, and advanced oxidation. Byproducts from inorganic such as chlorate and chloride associated with chlorine dioxide, and bromate that is associated with ozone and has also been found when chlorine dioxide is exposed to sunlight. So what it implies is that when chlorine dioxide is used for water treatment, we expect these two byproducts, chlorate and chloride. We monitor these two very well to be sure that all are removed from the treatment process. Otherwise, they are very dangerous. Some of them have been linked to cancer. At the same time, if we use ozone in water that constitutes carbonate and bicarbonate, then we expect bromate as a byproduct. Still, if the water is being treated with chlorine dioxide and exposed to sunlight, we expect the same bromate as a byproduct. Now, halogenated organic byproducts are formed when natural organic matter NOM reacts with free chlorine or free bromide. Free chlorine can be introduced to water directly as a primary or secondary disinfectant through chlorine dioxide or chloramines. Free bromine results from the oxidation of the bromide ion in source water. Factors affecting the formation of halogenated disinfection byproducts include the type and the concentration of natural organic matter, the oxidant type, and the dose, contact time, bromide ion concentration, the water pH, the organic nitrogen concentration in the water, and the water temperature. Now, if we are looking at non-halogenated disinfection byproducts, which are formed when strong oxidants reacts with organic compounds found in the water. Now, ozone and peroxone oxidation of organics leads to the production of aldehydes, aldo and keto acids, organic acids, and when bromide ion is present in the water, it produces brominated organics. Many oxidation byproducts are biodegradable and appear as biodegradable dissolved organic carbon, BDOC, and assimilable organic carbon, AOC, in treated water. Bromide ion plays a key role in disinfection byproduct formation. Ozone or free chlorine oxidizes bromide ion to hypobromate ion or hypobromous acid, which subsequently forms brominated disinfection byproducts. Brominated organic byproducts include compounds such as bromoform, brominated acetic acids and acetonitriles, bromopicrine, and cyanogen bromide. Only about 1/3 of the bromide ions incorporated into byproducts has been identified. Others are yet to be identified. Numerous researchers have documented that NOM is the principal precursor of organic disinfection byproduct formation. So what it implies is that it has been linked that natural organic matter is a principal precursor of organic disinfection byproduct formation. Chlorine reacts with natural organic matter to produce a variety of disinfection byproducts, including trihalomethanes, haloacetic acid, and others. Ozone reacts with natural organic matter to produce aldehydes, organic acids, and aldo and keto acids. Many of these are produced by chlorine as well. Now, considering the disinfection kinetics, Harriet Schick in 1908 discovered that the inactivation rate of microorganisms could best be described by a first-order reaction called Chick's law. And Chick's law is telling us about the time derivative of concentration of organism is equal to the rate constant multiplied by the initial concentration of the organism, or in n all over n naught is equal to minus k dot t, where n is equal to concentration of organism per meter cube, n naught is initial concentration of organism per meter cube, t is the time in seconds, k is the rate constant per second. The rate constant k differs per type and concentration of disinfectant, organism, and temperature. The sensitivity of an organism to a certain species depends on factors such as the penetration of the cell wall and the time needed to penetrate vital centers. According to Chick's law, the log removal can be doubled, providing the double of the contact time and considering that the disinfectant concentration is constant. It should be noted that Chick's law is the same formula for natural decay with an increased decay constant caused by disinfection. Due to the substantial amount of microorganisms involved in disinfection, log removal is used to talk about the efficiency of this treatment. The ratio of microorganisms inactivated to the original number be, for example, 99% stands for 2 logs, or 99.99% stands for 4 logs. Thank you for your attention. We expect you to follow us in our next teaching series. We have just looked at disinfection byproducts and some of the disinfectants. We looked at it from chemistry point of view. I hope you have gained something from this. Thank you.